Student, if you have any doubt, you can ask with the sir. After that, sir will start the tear down.
So during this part of the course, like from week 9 to 11, where we have discussed this system composition of, and means mainly we have taken the role of an embedded engineer or an architect, if I'm right. Right, but the means, and we have also understood that the role of an analog solution designer is more deep in it's more technical. I mean, has got more to do with the physical realization of components, so to say.
Okay, go on. So what is your question?
So question is that means parts like capacitance and inductance is a different thing, I believe. But how are these realized in form of ICs? Means resistance, and these are passive components, right? Capacitance and um, resistance. And why I'm asking you this means uh, analog filter design is something which we are learning in the first half of the course, and getting precise value of these components is quite critical in getting the response right for analog filters, as I understand. So yeah, my question is more towards a technical design of these things, but yeah, if you can throw some light on that aspect, how are those components realized on the ICs, so to say?
So, see, maybe I will give you two comments and then I will try to answer your question as well. Um, the I mean, the first half of the course really doesn't focus on filters per se, right? It is more about understanding how you build analog systems, understanding frequency responses, understanding stability. That is more the focus of what Professor Shanti taught, right? Understanding negative feedback, frequency response, stability, so on and so forth. So I wouldn't
Yes, sir.
really call that filter design. Filter design is far more complex than that, right? And both Professor Shanti and I feel that it is important for all of you to have understanding of the basic elements that go into complex system building. Right. For example, inductors, resistors, capacitors, they're basic elements that are used in any circuit you put together. The same way, some of these amplifiers, feedback amplifiers, are basic building blocks that are present in any system, any embedded system that you will put together. So the understanding of how an analog subsystem works, we feel is maybe more important than physical realization of components, right? That's more usually done more in a devices class, not necessarily in a circuits class. That said, in terms of components themselves, you can get very precision components now. It's just a trade-off between the cost you're willing to pay and the precision that you need. For most embedded systems, capacitors, inductors, they either do the purpose of decoupling or the purpose of a choke. So you wouldn't care so much about the accuracy itself. The only exception maybe is for an RF circuit, where for the matching network, you might care about exact values quite a bit, where even there some variation is acceptable. And these processes, I think, are pretty well defined in terms of what materials you use for the two plates, what material you use for the dielectric, where the variation comes from insofar as a capacitor is concerned. And for an inductor, what material you use for the coiling, how you control the number of turns of the coil, how you control the thickness of the wire you use, again, to be able to get control over the inductance. So it's not so much a technical problem in terms of oh, how do I get a 1% rated capacitor or a 1% rated inductor? It's more, that's going to be more expensive than a 5% rated component. Are you willing to pay that extra cost? Do you need to, do you really need that accuracy, right? So I would maybe, Gaurav, give you this advice also, that some of that is only, oh, this versus that, select is just about choosing what you need. That is not so critical. The factors that drive what spec you can accept is a far more important question, right? So how the system comes together, and okay, for this application, do I need so much performance? Can I do with lesser performance? What is the trade-off between them? That is, in my mind, a far bigger engineering problem for an analog system engineer or an embedded system engineer to solve. So that's the way we have structured the course. Long answer, but hopefully I answered your question.
Yes, sir. But my curiosity was more towards the miniaturization aspect. Like, means transistors, we have been able to shrink them to fit millions and millions of them on a single chip. Is there such a limit on the physical design of these passive components as well?
So see, the in terms of, so you take, for example, an SoC that has billions of transistors, right? Who provides the decoupling for all of those transistors that are switching? That decoupling also sits inside the SoC only. So now, if you take a PCB, you will see a lot of capacitors on the outside, and this is something we talked about, right? But those capacitors have a self-resonant frequency, which means they're really not usable. They're not going to give you great decoupling at high frequencies. The decoupling at high frequencies comes from the capacitance that is present on the die. So as geometry shrink, your ability to get more picofarad per millimeter square is better and better, because dimensions are shrinking, dielectrics are shrinking, which means that the unit area capacitance will increase. So that is also a byproduct of the density that you get as you go to lower geometry nodes. That's why you're able to get, pack billions of transistors and still be able to manage supply transients, and you think about it, no, it's billions of transistors. Each generation switches at maybe 50% more frequency. So the amount of decoupling that is needed keeps increasing. And that is all done through on-die capacitance. So I think, at least for capacitance, that's enough evidence that miniaturization is happening. Inductance is still, people still do trace inductance for small values. So if you look, for example, at radar, maybe 77 gigahertz RF radar, the inductance, the matching network there might be in the range of 100 picohenry to 500 picohenry, which might be traces on the chip. Because the kind of inductance value is small. So there again, you might be able to get very decent control. So I think for the purposes that they are used in, miniaturization has happened, is how I would at least read it.
Okay, sir. Yeah, got it. Uh,
Anybody else? Again, this is open forum. Okay, you can ask me anything you want.
Good
Did
evening,
any
sir.
of you have any other suggestions on what else we can do in the course? Was the course content okay? Did we miss something? Was there something that you thought, oh, this is good, this is not good?
Sir, a small query.
Huh.
Sir, in one of the weeks, where you are explaining the resistive voltage controller, I mean, the power management system, which we made
Huh.
with a resistive divider, there you
Huh.
have explained about the normalized some aspects from probability. and statistics.
Correct. Huh.
So I know it will the statistics is very used. I mean, very useful in communications domain. How well do we need as an embedded engineer?
See, statistics is a good question, Subhash. I think variability is part and parcel. I mean, you look at Gaurav's question also. No, it comes back to the same thing. Miniaturization will come with increased variability. Once you have increased variability, if you're shipping a million units, how do you make sure that all million units meet the performance that you promise? It is that sounds exactly like a statistics problem, right? I have 1 million parts. There is going to be some distribution of performance across those parts. How do I put bounds on those performance limits? So once you think about it that way, you will recognize that statistics is very critical, whichever aspect of electrical engineering you take up. So in the context of analog design, component matching, so maybe at some point you will start to look at so even now you take an amplifier, right? You assume that gain is 1 plus R2 by R1, but R2 and R1 are not exactly matched. There will be some mismatch between them, which means you get a certain bound on the gain. Now if you are very particular that that gain be exactly some number, or so let's say I'm building an LDO, right? Let's go back to what we had in the class itself. My I'm using a microcontroller. That microcontroller has a rated voltage of 1.8, and the chip supplier tells me, okay, it is 1.8, but it is you can't take it above 1.89, and below 1.71 I won't give you performance. So I have to achieve 1.8 plus minus 5%. Now that is going to drive what sort of components I use. If I want to ship again, what volume, what sort of component matching is needed. So understanding the correlation between component matching to the amount of variability I will see over a very large volume to what the chip supplier says they will support is a very integral part of decision making for the embedded system engineer. So I would think statistics knowledge is very critical.
Yes, sir. So, I mean, it means that in any component we choose, we have to keep in mind about these tolerances and the deviation.
Yes. I think variability, yeah, it doesn't matter whether you're an embedded system engineer or you're a VLSI engineer. VLSI engineers, in fact, are impacted far more by variation than embedded engineers because what will happen is, let's say you have, you generate a capacitor. So you let's say you go to advanced geometry, right? Advanced geometry, the metal lines are very narrow because that's the benefit of the advanced geometry, right? So now that the metal lines are very narrow, the variation in those metal lines is going to be much higher. So plus minus 50% type of variation is very possible. All of that has to be comprehended in the design. So a VLSI engineer will have, which means that now you think about it. No, let's say my gate length can vary because of the geometry size. My gate length can vary plus minus 30-40%, which means all of the parameters associated with that MOSFET are going to change by that much. So if I now built an analog circuit, that analog circuit, I have to say, okay, I have to support from minus 40 to 125 degrees C. I have to support from minimum supply to maximum supply, and I have to support across all of these geometry variations. So it is integral part of engineering across the board. VLSI designer, embedded system engineer, signal processing engineer, doesn't matter what your role is, that becomes very important.
Okay, sir. So it is like one of the basic subjects everyone should know.
Yes. So you guys do two math courses, huh? Two math classes are
Yeah.
there, no? Part of the
Yeah.
curriculum.
Yes, sir.
Yeah. Math is very important. Yeah. So statistics, and I'm sure I don't know. Andrew teaches that class, is it?
Yeah, but we were not introduced to statistics.
Oh, I see. Okay. Yeah. Okay. That is then I'll give them that feedback. Statistics should be part of the class.
Yes,
Sir,
sir.
it's an elective. So do you recommend that we should take that elective?
If there is a class on statistics, I would recommend that to anybody who wants to do engineering. I would say knowledge of statistics is very important. That is my personal view.
Okay, sir. Thanks, sir.
I will pass this feedback on to the team that at least some introduction to statistics So let's say you guys are familiar with this concept of Monte Carlo simulations and all that, right? At least to that degree, I think there is value in knowing the concepts. What is a normal distribution? What is standard deviation of a normal distribution? And then if you have, let's say, a normal distribution and a million parts, how many parts will fall outside 3 sigma? I think these are all good things, at least for every engineer to know. So I will also give this feedback to the team.
Yes, sir. This I have felt this lack in one more place. Like in one of the class, you said that okay, now you start. I mean, in the same lecture, you have said okay, now you start simulating it for million times and you see the deviation for yourself. Then, can you name what simulator you taught in the class?
I think PSpice, you can even do it in Excel if you want. See, Excel has a random function, right? Variation means what? Variation means that the correlation between any two parts is absent. It's all uncorrelated. So once you define a standard deviation, and you know the mean value of the resistor. So you can say that with a random function generator, generate 1,000 values for one resistor, 1,000 values for another resistor, and check 1 plus R2 by R1 or R1 by R1 plus R2 for this combination. Now you plot that, that will give you the variation in the voltage division.
Okay. Okay.
So even that much is enough. That will give you a sense of what sort of standard deviation. So suppose I say, okay, I'm supposed to generate, I can accept only 1% variation. Now you can play with the tolerance on the two individual components and see out of 1,000 how many fell outside the 1% bracket.
Yes, sir. Good, right.
You can do it in Excel. You can write a Python script.
Yes, sure. Thank you, sir.
Yes. Anything else, guys?
Hello, sir.
Hi, Muthu. Tell me.
Good evening, sir.
Good evening. Good evening.
Yes, sir. Sir, I have one suggestion to in the perspective of the course. I think adding some images or showing some actual components which we are learning in the course lectures itself, it will help us to visualize how the real component which we are learning will look like. So it will help us to understand how a real particle will actually are made.
Understood.
Yeah, that will
Understood,
be a very good.
Muthu. I follow. I agree also. I think Subhash raised the same point last week when we had the call. I understand. Input taken. I will see how to roll it in going forward. I'm going to show you something today. Hopefully that addresses the ask you have. And if you guys feel, oh, this is what we wanted to see, then we'll see how to integrate it into the course.
Okay. Yeah. Yes. Thank you, sir.
Any other questions or comments? Okay, so let's dive into what I wanted to show you guys. Hopefully the camera does a decent job of, let me move this back a little bit. Okay, so, ayyo, I'm sick. Let me see if I can widen this somehow. You can see only a piece of the product, no? You can't see the full tray, right? Or are you able to see the full tray?
So the
No,
video
sir.
is actually cut off.
Video is cut off, no? Okay, I don't know how to make it wider. That's okay, no worries. So, all right. Maybe I'll show it here. So this is our product. This is the product that we call C30. This is an intercom device that my company makes. You're able to see this, right?
Yes, sir.
So this is an intercom product that our company makes. So this opens something like this. So it has the intercom unit on the top, and then the rest that you see is a headset that goes into the helmet. So this is a device that you mount on the helmet. I'm going to show you the different pieces that go into it. Okay. So this is a device that you mount onto the helmet. At one level, it's a Bluetooth headset in that it allows you to listen to music, take and answer phone calls, get navigation assistance, invoke voice assistant, and you can also use it to connect to other riders. So it's also an intercom, has an intercom function. So if you're riding a motorcycle with three other friends on other motorcycles, you can keep talking to each other while you ride. That is what this product does. So this is the box. Let me now show you. Maybe I can just yeah, okay. So what you see here in the why is this not okay. Okay. So now you're able to see the tray, right? Whatever you see on the tray are essentially all the parts that go into making this product, right? So let me start with the different parts. So this is the, whatever you see here on the camera is the front housing unit, and then it also, there's also the corresponding back cover. So basically you think of it as these two go hand in hand, right? The front cover and the back housing. Then it has a 4-layer PCB which has components on both sides. So on this side, you can see the 5 buttons in those. So the 5 black dots you see are the 5 buttons. And then on the other side, we have the more complex ICs. So the ST microcontroller, the NRF microcontroller, the TI Bluetooth chip, the connectors for charging for audio are all part of this SoC. The audio codec is also part of this SoC. Right, that all goes into this chip, and you can see that the shape of this PCB pretty much matches the shape of the plastic, right? Because this has to go into that. The other electronic component we have is this thing. This is an external antenna. So I told you that the intent of this product is to allow you to have a conversation with your friends who could be on other motorcycles riding some distance away. So think of it as somebody is half a kilometer away, somebody is 1 kilometer away. You have to be able to talk to each other, which means the signal has to be boosted. And that reception is managed through this antenna. So this is a 2.4 gigahertz dipole antenna. This gets inserted into the plastic, right? This is actually, here is the so this is the antenna housing. Whatever part I just showed you essentially goes into this antenna housing. This looks bulkier because we have 2-3 variations of that dipole antenna. What I showed you is a thin one. There's also a thicker version. Then we have the battery. This is a lithium polymer battery, and it's a 950 or 1000 mAh battery. One thing you will notice here, okay, this has only 2 wires. So we have both batteries with 2 leads and batteries with 3 leads. So if you remember some of the discussion we had on the battery charger, the battery and ground are 2 of the leads. And in some cases, there is also a temperature sense a lead that comes from the battery, which is connected to a negative thermal coefficient resistor. So as the temperature increases, that voltage will drop. So that can be used. So if your battery heats up too much, you can sense that battery's temperature through that third lead and turn off the charging. So the charger we discussed in the class has that capability. In that case, this battery will have a third lead. Here you see two leads. If we want the TS capability also, the battery will have a third lead. Okay. Then we also have this we make as a subsystem. So I don't have the parts themselves. Let me, maybe the plastic is not. So it is mic plus left and right speakers. So stereo speakers plus the mic, and that comes with a it comes with a micro USB connector, right? And that micro USB connector will plug into the PCB. Wait, this also, let me just 1 second. Let me show you the PCB a little better. So, okay. So this is the charging port, the Type-C port. And the other port that you see is the micro USB port. So that's the two ports that you see on the product. And then, like I said, you can see the different chips. You can see three large chips. One of them is the TI Bluetooth controller. The next one is the ST MCU from ST Microelectronics. And then we also have a NRF. So we have two radios, one for Bluetooth connection to the phone, one for connecting with other riders. So it's the Nordic SoC that is used to connect to the other riders. If you look closely, you will also see here another antenna. So this is an on-trace antenna. So, somebody was talking about miniaturization, right? So it is also possible to generate the antenna on the PCB itself. That is done here for one of the radios. And then if you turn it around, you can see the 5 switches. So we have 5 controls. You can see those 5 switches. It's not possible to see the LEDs from this image, but the LEDs are also on this side. So this is the side that faces the consumer. This side is inside the plastic to the back, right? So this is the product we make. And, you look at the number of parts here. And I can, so this has all the minute parts that go in. I don't know why the camera is not focusing where I wanted to. So let me see if, just give me one. So here, we, yeah. So you can see all the small elements that go into the product, the screws, the hinges, the plungers. So there are, I think, about 40, even for a product of this complexity, there are 45, 46 elements that have to be assembled. That is assuming that the PCB already comes assembled. The PCB has another maybe 90 components. So the total number of child parts may be close to 150 for a product of this class. Right? So this is very quickly the product that we make. Again, if you guys have any questions, I'm happy to answer them. Any questions, guys?
Yeah, hello.
Yes.
Yeah, sir, I just want to know like how the communication between rider to rider is happening. Which protocol is there?
We built our own application layer on top of Bluetooth Low Energy. So Bluetooth Low Energy is the base protocol layer. On top of that base protocol layer, we've written our own application. So the application layer is proprietary and custom to us. The base protocol layer is BLE.
Okay, like is the communication is between like from the mobile to the device, and with mobile to mobile is the different protocol you are using, is it?
No, it is not mobile to mobile. It is mobile to device and device to device. Mobile to device is Bluetooth Classic.
Mhm.
Device to device is Bluetooth Low Energy.
And how the communication between like different riders are happening. I just want to ask.
No. When I say device to device, that is what I mean. Device to device is communication between different riders.
And what is the range of that thing?
This will be again with line of sight. You will get a kilometer.
Okay. Thank you.
So the external antenna that I showed, this piece,
Yeah, right.
that allows you to get that range as well.
Okay.
I answered your question.
Yes, sir. Thank you.
Cool.
Sir,
Yes.
apart from bike riding, in what other areas this is being used?
This is only for motorcycle riding. We make only motorcycle riding accessories. That's all we do.
And is it being sold only in India, or
This we
how
sell as
profitable
of
it?
now only in India. We just launched a newer version of the product that we might start to sell internationally. But this product we sell only in India.
Okay. Yeah, yes. Thanks.
Good evening, sir.
Hi, Krish.
Sir, what is the purpose of using a larger antenna when we can miniaturize it into the PCB itself?
The benefit of the larger antenna is that you will get better directivity gain. So on PCB antenna will have significant insertion loss. So let's say you have a power amplifier that is putting out some power. That power multiplied by the antenna's directivity is essentially the energy that you're radiating. That directivity will be low for an on for a PCB antenna. It will be far better for an external antenna. So it allows you to put more power. It allows you to receive better. So both ways you benefit, because the power you radiate is power amp power multiplied by directivity. The power you receive is directivity multiplied by LNA gain. So it's when you do end-to-end analysis, it is directivity square. So if you double the gain of the antenna, you are improving the overall performance of your system 4 times.
Okay, sir. Sir, one more thing. Through this course, we have understood what all are the different subsystems used in particular application. But how do we go about building from ground up?
So see, there are two aspects here. Okay, one is that's the distinction between what a VLSI designer does and what an embedded system engineer does. An embedded system engineer really doesn't. So an electronic systems engineer really doesn't build a regulator or build a battery charger. What an embedded system engineer will do is design an electronic system, design a product like what I'm showing you, using his or her knowledge of how these components come together. So at some level, we are all people who use these components and use it to build our system. So you take this PCB, for example. This PCB has a battery charger subsystem. It has a power management subsystem. It has an LED subsystem. It has a data converter subsystem. Then it has the microcontroller, the RF, so on and so forth. But without a high level understanding of how those systems work, it is very difficult to put together a system like this or a product like this. So for people who want to pursue a career path in electronic systems, right, I think it is important to also keep taking the system view. You don't need to build every component yourself. You need to have a working knowledge of the component to say, oh, okay, now I know how to choose one versus the other. My interest is really building systems like this. Right, so which is why we don't go too deep into how do you build an LDO, how do you compensate it, how do you look at stability, etc. We still take a control systems view of the regulator.
Okay.
Did I answer your question?
Yes, sir. Yes, sir. Thank you, sir.
Cool.
Hello, sir. Good evening, sir.
Hi, Aditya.
Sir, I will be taking the analog electronics course in the next term, but I have a question out of curiosity. First of all, sir, you did a wonderful explanation. Thanks for that. And sir, like you said about that, the communication between driver to driver, right? So, sir, is the communication medium dependent?
Is
Medium
it
dependent,
medium? Uh,
medium dependent
is
in the sense, like in the air, or like can the communication happens in the water as well?
So it can happen in water also, but water is a far more lossy medium than air. So the same thing when you try in water, the range will be much lesser. It will still work, but the range will be much lesser. So in fact, why even go to water? On a dry day versus a day with a lot of moisture, there will be difference in range.
Okay, but sir, like I was thinking that in the water, scuba divers also communicate between them. So we can improve this like antenna so that the scuba divers can also use this particular thing.
Yeah, I mean, if the economics of that market is interesting enough, yes.
So you're saying that so is that like I think that they also use some kind of system to communicate between them, right? So is that particular system much more costly, or is that system less
So there
costly?
are two, three things. Okay, one is now let's say we are building a wireless communication system. It is possible to build it in many different ways. You can say that okay, I'm going to build it. I'm not worried too much about power. I want a range in water. So what I will do is I will build it to be. So right now we put out 100 milliwatt of power. Somebody can say no, no, I'm not 100 milliwatt. I want good range in water, so I will put a 1 watt power amplifier instead of 20 dBm, 30 dBm. So I will get more range. Very possible, right? The thing comes not so much from how to say this. The size of the market for a product dictates how commonplace the design becomes. So cost also is a function of, for example, cell phones today are very cheap because everybody buys them. So the component price comes down. So it's
Correct.
not a niche market anymore. You get the economics that come with a mass market. Something like what we are doing, which is for motorcycles, two wheelers. India is the largest market in the world, so there again, you start to see some economy of scale. So it's not truly a mass market, but it's not a super niche market either. Scuba diving, at least in the Indian context, will be super niche market, right? And somebody made this point. Obviously, the product, by the way, what I showed you is waterproof. It is IP67 rated, so technically you can go up to 1 meter deep and use it. But for scuba diving, you might need something that is IP68 rated. IP68 rating means you can go down 100 feet, I think. So 30 meters deep in water you can go, and the product will still be okay. Pressure increases as you go deeper and deeper, right? So IP68 is what the product will need to be rated for, if not something even more aggressive. So I would think solutions are not commonplace because maybe the market is very small. That said, these are the technical things to keep in mind.
Okay, sir. Thank you, sir. Got it.
Yes.
Hello, sir.
Hi, Akhilesh.
Yeah, so I just searched for the thing you just told, like Bluetooth. So it have a range of 100 meters, and you are achieving 1 kilometer range. So how is it possible? I just want to know.
No, no, Bluetooth per se doesn't have a fixed range, Akhilesh. I mean, don't couple the standard with range. They are two different
Mm-hmm.
things, right? The standard defines how two devices will communicate. Now, as you put more power, you will get more range. Which is why I was saying our base protocol layer is Bluetooth Low Energy. The application layer, the physical layer are all proprietary to us. So we put higher power to be able to get the range. The protocol is just the handshake between the devices to make sure communication is smooth.
Uh, but the similar thing is happening with the 5G also, right? In 5G communication, there's a thing like we don't get that much range as 4G or something, right? So is it somehow possible that we will increase the power of this thing and make it having a very greater range or something?
No, see, beyond a point, the level of interference becomes so. Maybe it's not fair to compare what we do with cellular telephony, because
Hmm.
cellular telephony, the density is so high that there might be other limits to range, right? Also,
Okay.
with cellular telephony, 5G and all, throughput is extremely high. There is a trade off between throughput and range. So, if you drop the throughput to 1/10, you might get much more range with cellular telephony, and in general you will get with every application. So I think it's not so much a okay 5G, I put more power, I will get more range. Theoretically, yes, but if you put more power, everybody around you is also putting more power. The whole network is so dense that you are now limited by interference from other devices. If it was only you transmitting to one other, let's say you're the only person in that town, you have a mobile tower to yourself, then yeah, if you increase the power, you will get more range. But it's probably 100,000 people who are using that same mobile tower, if not more. So if all of you increase the power, your power went up, your interferer's power went up. So the SNR really doesn't get better, which means you won't get more range.
Okay. Like we have to consider all the things like what is the range we need, what is the interference we have, and all, right?
Correct. And interference is very very dependent on density. I mean, you imagine, no, if a mobile tower is serviced by how many, is services how many people? At least 100,000 people. So now
Right.
all of them are, you assume there's still some time division, etc., who transmits when, but still
Hmm.
the total amount of RF energy in that spectrum at any given time is very high. So increasing everybody's power is really not going to achieve anything.
Okay. Okay, sir. Thank you for the explanation.
Oh, cheers, man. No worries.
Yeah.
Sir,
Huh.
if assume a case where we are using this device for multiple
Sorry, I'm not able to hear you now. I don't know what happened on my, I don't know if there's a problem on my side, but I can't hear you.
No, sir, I think Pratham have some network issues.
Okay, Pratham, we are not able to hear you. You might need to repeat what you said. You might maybe drop and come back. I don't know.
Sir, in the meanwhile, can I ask a
Ah,
question?
yes, Subhash.
Sir, yeah, you said that you are using BLE, the low energy version of Bluetooth in device to device communication. So, what is the trade-off we'll be facing there?
So the
Because we are
trade-off
not going
is
to use it.
similar. Okay, any wireless network you take, the trade-off comes from what are the interface. So Bluetooth low energy or Bluetooth in general uses the 2.4 to 2.5 gigahertz band. So it competes with other Bluetooth devices for slots, both in terms of time and in terms of frequency. It competes with Wi-Fi, again in terms of slots for time, slots for frequency. So both of these will be interferers. Now, if you're using a 4G device, 4G band 40, I think, is right next to the Bluetooth band. So these will be the different classes of interferers that you have to fight against. Now, so that is one side of the problem. The second side of the problem is if you want range, if you don't transmit enough power because of dispersive loss in the medium, the signal won't even reach the other person. So you have to put enough power, and then you have to be cognizant of all the other interferers that come. And then standards bodies also mandate how much power you can put. Because if, let's say, a Wi-Fi signal or a Bluetooth signal or a 4G signal is an interferer to you, you are an interferer to them. So what the standards body does is say that, okay, if you're operating in this band, this is the average, maximum average power you can put out. So those are defined both for FCC and CE standards, which limit the amount of power you can put. So within those limits, you would want to operate at maximum power to get the best range possible.
So, okay, here we are using the low energy Bluetooth version to get more range.
So don't get too hung up on the low energy and all that. Okay, it's just BLE we went with because it is used in billions of devices. So the standard is very robust. We don't really stick to the low power part because
Okay,
we are getting range, we are putting high power, but we are just reusing the standard from a protocol perspective.
okay. Then how is this different from the regular Bluetooth we use?
Because the protocol itself is different in how it manages connections, how it manages advertisement, how it manages reconnection, how it resolves low SNR conditions, which is why that requires also a fair bit of protocol understanding. But they are completely different standards. The
Okay, sir.
throughput is also different.
Okay, sir.
Hello, sir.
Yes, Pratham.
Sorry for disconnecting. What I wanted to ask was if this device is to be repurposed or redesigned for a sensitive application like medicine, emergency, or even military, how much would the design parameters would change? Is just increasing the accuracy of the some regulators and capacitors is enough, or we need to do some more changes to?
That is an interesting question, Pratham. See, there are two, three factors that you have to keep in mind. One is the level of reliability and the type of standard bodies or standards that you have to comply with for whatever product you're building. Let's say you're building something for medical application. Obviously, it needs to pass any stringent requirement that the medical body certification agency imposes. Because now this could technically be in a life and death scenario. So it is important that it adhere to those safety standards, right? So standards associated with your specific intended use is one consideration. Then the electronic parameters for design, which may be accuracy, what type of information you're exchanging or trying to give, so on and so forth. Right. I would think the standards body is where I would pay a lot more attention, particularly if you're talking spaces like medical. So the FDA rating or approval from FDA is very difficult to get. I don't know what other standards are there for something. Let's say a medical device that you want to build for use in the US.
Yeah, so but the reason I got this question was because in many components, at least the older ones, they have a military version. So like 7400, that is the standard 5400, which is the military standard. So they have higher parameters. So just replacing uh, commercial parts with military or some medical standard parts, would that technically suffice if assuming the standards and everything is rest is met?
No, but that is a start. See, so if you take military, for example, military applications require a wider temperature range to be supported than commercial applications. So if your commercial application, you can say maybe minus 10 to 85 degrees C is what I will support. If it's industrial, maybe minus 20, minus 25 to 105 or so. If it's military, typically people will support minus 50 to 100 plus, right? The lower temperatures become very critical to support as well. So the starting point is to use military graded parts. So each one of the components that you choose for an application will need to be military grade to make sure that there is no failure in these conditions. On top of that, you will need to see again, once you're using military grade components, what are the standards that you need to pass to say that your product is rated for a military grade application? So that's what I said. I would break it into two parts. One is again comes back to component selection that keeps in mind the intended use case, and then the certification or qualification you need to pass to say that your product is compliant for usage in that application.
Okay, so thank you, sir. So I have another one related
Ah,
to this. I have like it is available in online where you can see some of the internal views of some missiles and aerospace parts and all. The designs for them have not changed in 30, 20 years. So you have so imagine a rocket is being launched yesterday. If you open it, it will have same circuitry it had just 70 years or 50 years ago. So why is these things are not being modernized, even though we have all these facilities and much better hardware than the older ones?
that the first statement you made might not be correct, Pratham. It is not correct to say that components haven't changed, uh, uh, particularly for for fight for missiles, for anything that has feedback based on accuracy and range. 100% newer and newer components are used. Component certification takes longer. So, if, for example, for consumer, let's say an Apple iPhone might use a chip that was designed last year. A military grade application might use components that were designed maybe 2 3 years ago, because the certification qualification cycle is that much longer. But that's all it is. It's not, definitely not 40 50 years and all. I mean, you look at it, no, they're just the
Yeah, one example.
intercontinental. You take an intercontinental ballistic missile, for example, the range has increased how much over these years? What makes that possible? Electronics has to support that, no?
Yes, sir. So actually, like for
Both
an
both
example,
in
I just
terms
want
of
to give.
I mean, you think about it, range has gotten better, object detection has gotten better, targeting has gotten better. All of that is possible only if the electronics and the software supports it.
So like just for example, the Perseverance rover, which is on Mars right now, it's using a CPU from 2000. It is radio hardened and all, but it is still using some 20 years back older technology. So I'm talking more reference to that.
It might be in the context of, for that application, that much hardware is enough. I'm sure if you look into some of the hyperspectral imaging cameras that go on satellites today, they will use very advanced electronics. I think it's just a matter of where you look. That's all.
Okay, sir. Thank you.
Yes. We have 5 more minutes, guys. Any other questions?
Sir,
Yes.
so how crucial the software components or software part in this?
See,
Or
if you're building an embedded system, then obviously software is very important, right? So there is uh, there's hardware design, where analog system design plays a very important role. Then there is firmware design. Let's say you want your device to do some functions. Now you have to code your microcontroller to be able to execute those functions. And the different subsystems of your system all have to work together. So even something as simple as, when I turn on the device, I want my LED to flash a certain way. That's also a firmware problem, correct? So the how well you write your firmware is a very important aspect of product development. Now, if you also offer an app, then that app has to be in sync with the firmware. So that also has to be given due consideration.
yeah, yes, sir. And which one is used in this intercom? Or
We use an ST microcontroller. I think it's an M4 Cortex microcontroller, right, that houses some of our algorithms.
okay, yeah, yes, sir. Thank you.
Sir, are you also using some type of central processing unit which controls each and every of these components like ICs, Bluetooth, and all?
Uh, um, I wouldn't say yes or no. We do have the microcontroller, which is central to the whole product. But the Bluetooth controllers also have a fair bit of intelligence to be able to self-regulate themselves. The central processing unit, maybe not, I wouldn't call it a central processing unit. Maybe it's the central coordination unit in our design. So it does some algorithms, but it also does the job of coordinating between the different radios to ensure that the system operates properly?
Because sir, like currently we are also designing a particular system in which we are coordinating several components like motors and two different sensors, IR sensor and line following sensor, and which are connected to the FPGA. And on the FPGA, we designed a RISC-V CPU, which is based on Verilog. So using that particular CPU, we are controlling all the sensors. So I am asking in that context.
In that context, it is very similar. So the
Okay.
LED subsystem talks to the MCU. The Bluetooth subsystem talks to the MCU. The intercom subsystem talks to the MCU. Battery charging talks to the MCU. Button subsystem talks to the MCU. So the MCU is, in that sense, very central. It's very similar to what you explained.
Okay, sir. So, sir, like, are you following any particular architecture? So, which is a standard architecture?
No, in our case, we just use the interfaces available in the MCU and work with those interfaces. So if you use an SPI interface for one communication, then you just stick to the SPI standard. So we use SPI I2C, bunch of different interfaces for communication between the chips.
Okay, sir. Thank you, sir.
Cool. Maybe one last question before we stop.
Yes, sir. I had a question about audio transfer over Bluetooth.
Huh.
So, sir, in classical Bluetooth, I am aware of audio codecs like AAC and SBC and all. So, are these codecs the same in Bluetooth low energy as well, or is there some difference?
See, for Bluetooth connection to the phone, we use a classic connection. So what we have is an SBC codec. Over BLE, we do voice, where again we reuse the SBC codec.
Okay, so SBC is supported by both the classical and BLE.
See, BLE is only protocol. No, the application layer is ours. The codec and all runs on the application layer, right? So, and it's our device talking to our device. So we are free to do whatever codec we want.
Okay, all right.
See,
And sir,
standardization is needed when you have to connect to anybody else's device, right? If you're only connecting to your own device, then you can choose whatever standard you want.
okay, sir. Sir, I read in an article somewhere, it might be wrong, but I've heard that like a high quality audio transfer via Bluetooth happens on the classical version of Bluetooth and not on BLE. Is that correct? Or
That is not correct. There is no compression coding. The codec called the LC3 codec. The LC3 codec runs over BLE and gives you very good. So when they see there is the standard called LE audio, right? LE audio is now supported on some phones. It is audio over Bluetooth low energy, which uses the LC3 codec, and there is no compromise to quality. It sounds very good.
okay, sir. Thank you.
Okay, cool, guys. Thank you so much. Ankit, anything you want to say?
No, sir. No, sir.
Okay, cool, guys. Thank you so much. If there's anything else, you let Ankit know. He will pass on the message to me. I'm happy to tell you whatever you want to know.
Thank you, sir. Thanks for your time.
Thank you, sir.
Okay,
Thank
thanks,
you for the
guys.
session.
Take care.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.